right, welcome everyone to an introduction to artificial intelligence with Python. My name is Brian Yu, and in this class, we'll explore some of the ideas and techniques and algorithms that are at the foundation of artificial intelligence. Now, artificial intelligence covers a wide variety of types of techniques. Anytime you see a computer do something that appears to be intelligent or rational in some way, like recognizing someone's face in a photo, or being able to play a game better than people can, or being able to understand human language when we talk to our phones and they understand what we mean and are able to respond back to us, these are all examples of AI, or artificial intelligence. And in this class, we'll explore some of the ideas that make that AI possible. So we'll begin our conversations with search, the problem of we have an AI, and we would like the AI to be able to search for solutions to some kind of problem, no matter what that problem might be, whether it's trying to get driving directions from point A to point B, or trying to figure out how to play a game, given a tic-tac-toe game, for example, figuring out what move it ought to make. After that, we'll take a look at knowledge. Ideally, we want our AI to be able to know information, to be able to represent that information, and more importantly, to be able to draw inferences from that information, to be able to use the information it knows and draw additional conclusions. So we'll talk about how AI can be programmed in order to do just that. Then we'll explore the topic of uncertainty, talking about ideas of what happens if a computer isn't sure about a fact, but maybe is only sure with a certain probability. So we'll talk about some of the ideas behind probability and how computers can begin to deal with uncertain events in order to be a little bit more intelligent in that sense as well. After that, we'll turn our attention to optimization, problems of when the computer is trying to optimize for some sort of goal, especially in a situation where there might be multiple ways that a computer might solve a problem, but we're looking for a better way, or potentially the best way, if that's at all possible. Then we'll take a look at machine learning, or learning more generally, and looking at how, when we have access to data, our computers can be programmed to be quite intelligent by learning from data and learning from experience, being able to perform a task better and better based on greater access to data. So your email, for example, where your email inbox somehow knows which of your emails are good emails and which of your emails are spam. These are all examples of computers being able to learn from past experiences and past data. We'll take a look, too, at how computers are able to draw inspiration from human intelligence, looking at the structure of the human brain and how neural networks can be a computer analog to that sort of idea, and how by taking advantage of a certain type of structure of a computer program, we can write neural networks that are able to perform tasks very, very effectively. And then finally, we'll turn our attention to language, not programming languages, but human languages that we speak every day, and taking a look at the challenges that come about as a computer tries to understand natural language, and how it is that some of the natural language processing that occurs in modern artificial intelligence can actually work. But today, we'll begin our conversation with search, this problem of trying to figure out what to do when we have some sort of situation that the computer is in, some sort of environment that an agent is in, so to speak, and we would like for that agent to be able to somehow look for a solution to that problem. Now, these problems can come in any number of different types of formats. One example, for instance, might be something like this classic 15 puzzle with the sliding tiles that you might have seen, where you're trying to slide the tiles in order to make sure that all the numbers line up in order. This is an example of what you might call a search problem. The 15 puzzle begins in an initially mixed up state, and we need some way of finding moves to make in order to return the puzzle to its solved state. But there are similar problems that you can frame in other ways. Trying to find your way through a maze, for example, is another example of a search problem. You begin in one place, you have some goal of where you're trying to get to, and you need to figure out the correct sequence of actions that will take you from that initial state to the goal. And while this is a little bit abstract, anytime we talk about maze solving in this class, you can translate it to something a little more real world, something like driving directions. If you ever wonder how Google Maps is able to figure out what is the best way for you to get from point A to point B and what turns to make at what time depending on traffic, for example, it's often some sort of search algorithm. You have an AI that is trying to get from an initial position to some sort of goal by taking some sequence of actions. So we'll start our conversations today by thinking about these types of search problems and what goes into solving a search problem like this in order for an AI to be able to find a good solution. In order to do so, though, we're going to need to introduce a little bit of terminology, some of which I've already used. But the first term we'll need to think about is an agent. An agent is just some entity that perceives its environment. It somehow is able to perceive the things around it and act on that environment in some way. So in the case of the driving directions, your agent might be some representation of a car that is trying to figure out what actions to take in order to arrive at a destination. In the case of the 15 puzzle with the sliding tiles, the agent might be the AI or the person that is trying to solve that puzzle, to try and figure out what tiles to move in order to get to that solution. Next, we introduce the idea of a state. A state is just some configuration of the agent in its environment. So in the 15 puzzle, for example, any state might be any one of these three, for example. A state is just some configuration of the tiles, and each of these states is different and is going to require a slightly different solution. A different sequence of actions will be needed in each one of these in order to get from this initial state to the goal, which is where we're trying to get. So the initial state then, what is that? The initial state is just the state where the agent begins. It is one such state where we're going to start from. And this is going to be the starting point for our search algorithm, so to speak. We're going to begin with this initial state and then start to reason about it, to think about what actions might we apply to that initial state in order to figure out how to get from the beginning to the end, from the initial position to whatever our goal happens to be. And how do we make our way from that initial position to the goal? Well, ultimately, it's via taking actions. Actions are just choices that we can make in any given state. And in AI, we're always going to try to formalize these ideas a little bit more precisely, such that we could program them a little bit more mathematically, so to speak. So this will be a recurring theme. And we can more precisely define actions as a function. We're going to effectively define a function called actions that takes an input s, where s is going to be some state that exists inside of our environment. And actions of s is going to take this state as input and return as output the set of all actions that can be executed in that state. And so it's possible that some actions are only valid in certain states and not in other states. And we'll see examples of that soon too. So in the case of the 15 puzzle, for example, there are generally going to be 4 possible actions that we can do most of the time. We can slide a tile to the right, slide a tile to the left, slide a tile up, or slide a tile down, for example. And those are going to be the actions that are available to us. So somehow our AI, our program, needs some encoding of the state, which is often going to be in some numerical format, and some encoding of these actions. But it also needs some encoding of the relationship between these things. How do the states and actions relate to one another? And in order to do that, we'll introduce to our AI a transition model, which will be a description of what state we get after we perform some available action in some other state. And again, we can be a little bit more precise about this, define this transition model a little bit more formally, again, as a function. The function is going to be a function called result that this time takes 2 inputs. Input number 1 is s, some state, and input number 2 is a, some action. And the output of this function result is it is going to give us the state that we get after we perform action a in state s. So let's take a look at an example to see more precisely what this actually means. Here's an example of a state of the 15 puzzle, for example. And here's an example of an action, sliding a tile to the right. What happens if we pass these as inputs to the result function? Again, the result function takes this board, this state, as its first input, and it takes an action as a second input. And of course, here, I'm describing things visually so that you can see visually what the state is and what the action is. In a computer, you might represent one of these actions as just some number that represents the action. Or if you're familiar with enums that allow you to enumerate multiple possibilities, it might be something like that. And this state might just be represented as an array or 2-dimensional array of all of these numbers that exist. But here, we're going to show it visually just so you can see it. But when we take this state and this action, pass it into the result function, the output is a new state. The state we get after we take a tile and slide it to the right, and this is the state we get as a result. If we had a different action and a different state, for example, and pass that into the result function, we'd get a different answer altogether. So the result function needs to take care of figuring out how to take a state and take an action and get what results. And this is going to be our transition model that describes how it is that states and actions are related to each other. If we take this transition model and think about it more generally and across the entire problem, we can form what we might call a state space, the set of all of the states we can get from the initial state via any sequence of actions by taking 0 or 1 or 2 or more actions in addition to that. So we could draw a diagram that looks something like this, where every state is represented here by a game board. And there are arrows that connect every state to every other state we can get to from that state. And the state space is much larger than what you see just here. This is just a sample of what the state space might actually look like. And in general, across many search problems, whether they're this particular 15 puzzle or driving directions or something else, the state space is going to look something like this. We have individual states and arrows that are connecting them. And oftentimes, just for simplicity, we'll simplify our representation of this entire thing as a graph, some sequence of nodes and edges that connect nodes. But you can think of this more abstract representation as the exact same idea. Each of these little circles or nodes is going to represent one of the states inside of our problem. And the arrows here represent the actions that we can take in any particular state, taking us from one particular state to another state, for example. All right. So now we have this idea of nodes that are representing these states, actions that can take us from one state to another, and a transition model that defines what happens after we take a particular action. So the next step we need to figure out is how we know when the AI is done solving the problem. The AI needs some way to know when it gets to the goal that it's found the goal. So the next thing we'll need to encode into our artificial intelligence is a goal test, some way to determine whether a given state is a goal state. In the case of something like driving directions, it might be pretty easy. If you're in a state that corresponds to whatever the user typed in as their intended destination, well, then you know you're in a goal state. In the 15 puzzle, it might be checking the numbers to make sure they're all in ascending order. But the AI needs some way to encode whether or not any state they happen to be in is a goal. And some problems might have one goal, like a maze where you have one initial position and one ending position, and that's the goal. In other more complex problems, you might imagine that there are multiple possible goals, that there are multiple ways to solve a problem, and we might not care which one the computer finds, as long as it does find a particular goal. However, sometimes a computer doesn't just care about finding a goal, but finding a goal well, or one with a low cost. And it's for that reason that the last piece of terminology that we'll use to define these search problems is something called a path cost. You might imagine that in the case of driving directions, it would be pretty annoying if I said I wanted directions from point A to point B, and the route that Google Maps gave me was a long route with lots of detours that were unnecessary, that took longer than it should have for me to get to that destination. And it's for that reason that when we're formulating search problems, we'll often give every path some sort of numerical cost, some number telling us how expensive it is to take this particular option, and then tell our AI that instead of just finding a solution, some way of getting from the initial state to the goal, we'd really like to find one that minimizes this path cost, that is less expensive or takes less time or minimizes some other numerical value. We can represent this graphically if we take a look at this graph again and imagine that each of these arrows, each of these actions that we can take from one state to another state, has some sort of number associated with it, that number being the path cost of this particular action, where some of the costs for any particular action might be more expensive than the cost for some other action, for example. Although this will only happen in some sorts of problems. In other problems, we can simplify the diagram and just assume that the cost of any particular action is the same. And this is probably the case in something like the 15 puzzle, for example, where it doesn't really make a difference whether I'm moving right or moving left. The only thing that matters is the total number of steps that I have to take to get from point A to point B. And each of those steps is of equal cost. We can just assume it's of some constant cost, like 1. And so this now forms the basis for what we might consider to be a search problem. A search problem has some sort of initial state, some place where we begin, some sort of action that we can take, or multiple actions that we can take in any given state, and it has a transition model, some way of defining what happens when we go from one state and take one action, what state do we end up with as a result. In addition to that, we need some goal test to know whether or not we've reached a goal, and then we need a path cost function that tells us for any particular path, by following some sequence of actions, how expensive is that path? What is its cost in terms of money or time or some other resource that we are trying to minimize our usage of? And the goal ultimately is to find a solution, where a solution in this case is just some sequence of actions that will take us from the initial state to the goal state. And ideally, we'd like to find not just any solution, but the optimal solution, which is a solution that has the lowest path cost among all of the possible solutions. And in some cases, there might be multiple optimal solutions, but an optimal solution just means that there is no way that we could have done better in terms of finding that solution. So now we've defined the problem. And now we need to begin to figure out how it is that we're going to solve this kind of search problem. And in order to do so, you'll probably imagine that our computer is going to need to represent a whole bunch of data about this particular problem. We need to represent data about where we are in the problem, and we might need to be considering multiple different options at once. And oftentimes, when we're trying to package a whole bunch of data related to a state together, we'll do so using a data structure that we're going to call a node. A node is a data structure that is just going to keep track of a variety of different values. And specifically, in the case of a search problem, it's going to keep track of these 4 values in particular. Every node is going to keep track of a state, the state we're currently on. And every node is also going to keep track of a parent being the state before us, or the node that we used in order to get to this current state. And this is going to be relevant because eventually, once we reach the goal node, once we get to the end, we want to know what sequence of actions we used in order to get to that goal. And the way we'll know that is by looking at these parents to keep track of what led us to the goal, and what led us to that state, and what led us to the state before that, so on and so forth, backtracking our way to the beginning so that we know the entire sequence of actions we needed in order to get from the beginning to the end. The node is also going to keep track of what action we took in order to get from the parent to the current state. And the node is also going to keep track of a path cost. In other words, it's going to keep track of the number that represents how long it took to get from the initial state to the state that we currently happen to be at. And we'll see why this is relevant as we start to talk about some of the optimizations that we can make in terms of these search problems more generally. So this is the data structure that we're going to use in order to solve the problem. And now let's talk about the approach. How might we actually begin to solve the problem? Well, as you might imagine, what we're going to do is we're going to start at one particular state, and we're just going to explore from there. The intuition is that from a given state, we have multiple options that we could take, and we're going to explore those options. And once we explore those options, we'll find that more options than that are going to make themselves available. And we're going to consider all of the available options to be stored inside of a single data structure that we'll call the frontier. The frontier is going to represent all of the things that we could explore next that we haven't yet explored or visited. So in our approach, we're going to begin the search algorithm by starting with a frontier that just contains one state. The frontier is going to contain the initial state, because at the beginning, that's the only state we know about. That is the only state that exists. And then our search algorithm is effectively going to follow a loop. We're going to repeat some process again and again and again. The first thing we're going to do is, if the frontier is empty, then there's no solution. And we can report that there is no way to get to the goal. And that's certainly possible. There are certain types of problems that an AI might try to explore and realize that there is no way to solve that problem. And that's useful information for humans to know as well. So if ever the frontier is empty, that means there's nothing left to explore, and we haven't yet found a solution, so there is no solution. There's nothing left to explore. Otherwise, what we'll do is we'll remove a node from the frontier. So right now, at the beginning, the frontier just contains one node representing the initial state. But over time, the frontier might grow. It might contain multiple states. And so here, we're just going to remove a single node from that frontier. If that node happens to be a goal, then we found a solution. So we remove a node from the frontier and ask ourselves, is this the goal? And we do that by applying the goal test that we talked about earlier, asking if we're at the destination, or asking if all the numbers of the 15 puzzle happen to be in order. So if the node contains the goal, we found a solution, great, we're done. And otherwise, what we'll need to do is we'll need to expand the node. And this is a term of art in artificial intelligence. To expand the node just means to look at all of the neighbors of that node. In other words, consider all of the possible actions that I could take from the state that this node is representing, and what nodes could I get to from there. We're going to take all of those nodes, the next nodes that I can get to from this current one I'm looking at, and add those to the frontier. And then we'll repeat this process. So at a very high level, the idea is we start with a frontier that contains the initial state, and we're constantly removing a node from the frontier, looking at where we can get to next, and adding those nodes to the frontier, repeating this process over and over until either we remove a node from the frontier and it contains a goal, meaning we've solved the problem, or we run into a situation where the frontier is empty, at which point we're left with no solution.